Today we're going to talk about printing hundreds of assemblies, 3D printing these assemblies, and how much, what it taught us about performing low to mid-volume production in manufacturing. My name is Marcus, that is Bryce, and Kyle's somewhere in the background. This is another project we were doing, but basically, we're constantly trying to push the envelope on 3D printing, trying to learn just how capable this material and these parts can be. So this is doing us some load testing. But today, what we're focused on is something I needed, which was promotional giveaways. So I'm working marketing now. I'm kind of the technical marketing person. We do giveaways for live events, and with 3D printing, it makes it perfect because you can just print something that is illustrative of the capabilities of 3D printing, and it's kind of a cool thing to keep, and it also shows off the possibilities. Now, normally we would do promotional giveaways like hats and shirts and beer koozies, and we've done that. We've done a lot of that actually. Usually shirts are the biggest difficulty because they're not universal, right? It is easy to brand or customize them with either screen printing or embroidery. We want to find something that's small, easy to ship, easy for people to carry home, right? So that kind of limits us in the types of things we might be able to do. We want something to be functional and durable. And so some of the things we've done in the past are like these bottle opener keychains. Notice there's an embedded nickel in this, and that embedded hardware shows that with strong plastic parts, even if they're doing highly abrasive things like opening beer bottles, as long as you have some inserted metal parts, some kind of a hybrid part, it's going to run really well. Then we got the Metal X, and we started printing these. This is a stainless steel 3D printed piece. This is one of the early ones. The finish is really cleaned up a lot on the later ones. And it wasn't a lot of material, but what ended up happening was because you have to lay these out flat, both of these were extremely operator intensive. In the case of the embedded hardware, they had to start the print, and then after, maybe an hour, they'd have to go and put the nickels in and then continue the print and then take all the pieces off the bed and start the whole process over. So you were constantly going back, checking the machine and doing a little bit of work. For the metal, you only had what was in the print surface area that you could make. And then the real limiting factor was the center oven. These had to be laid out flat in the center oven, and short of making a custom center plate, we could only run a certain number. So they ended up getting kind of expensive just in the post-processing. During COVID, we came up with an idea to create some giveaways, some little door pullers. So this has a lot of different features to help you interact with things in public without touching them. But of course, we didn't have any live events during COVID, so that never really happened. So the goal was to create something interesting and new, something affordable. $20, you can usually get a hat or a shirt, but those are not the most personal items. So we're trying to keep it below $20, as low as possible, with minimal labor costs. We want the labor cost involved in that price. And the big one is we want to demonstrate the capabilities of that Formlabs Fuse 1 Plus 30 watt. So in order to do that, we are going to need to know more about the Fuse 1 Plus. So Bryce, why don't you take us through a little overview of the system?
All right, so Marcus has done a great job setting the stage here. If you're an engineer or you work in manufacturing, you might have gotten one of those emails where you're just scratching your head because someone sent over a crazy part file, or maybe it's just like an artistic rendering, and you have no idea how you're supposed to make that part. And that's probably one of my favorite things about SLS, is because you just have so much freedom with SLS. And Marcus and I are getting along much better now that we have this technology, and we can make all of these crazy parts that he's asking for. So what is SLS and how does it work? SLS stands for Selective Laser Sintering, which is a 3D printing process, but it looks and performs a lot different than what most people picture when it comes to a 3D printer. With SLS, you're using a plastic powder instead of a pre-extruded filament on a spool or a liquid resin. So how do you print with a plastic powder though? Well, to print you actually have a build chamber that sits inside of this thing, and the build chamber gets covered with a really flat layer of powder, and that powder gets melted by a laser. So the cross section of your part is being embedded into this powder. And this is sort of a look at what the process looks like from the onboard camera inside of the printer. And there are a few major benefits to this process. The big one we're talking about here today is the design freedom, because SLS has very few design constraints. And a big part of that is because your parts are fully supported in every direction by unfused powder. And so you can kind of think about it like sand casting, where your part is sort of packed inside of this unfused powder. Except in this case, that unused powder actually gets recycled back into the system for future prints. And you can also get much finer detail than a sand casting because you're drawing your part out with a really fine laser. That laser also gives you a really good surface finish with almost invisible layer lines. And your parts are supported in every direction, so now you can print in all 3 dimensions, so you can stack parts above each other or even nest a part inside of another part. And in this video, you can probably see how quick a whole layer is printed. And so if you combine that speed, the quantity of parts that you can get out of a build, and that ability to recycle unused material, you can get a ton of parts for a very reasonable cost. And that's without worrying about any upfront fees like an injection mold or any other startup costs that you may encounter. Plus, you can print multiple parts at one time. So hopefully you can start to see why we get so hyped about this technology. It can just really open up a lot of doors, and it's a lot of fun to use because of that design freedom. All right, so that's all great, but how do you get your parts out of that powder and have them ready to go? Well, you can buy a printer by itself, and it comes with a depowdering bucket, but really the best and most hands-off way to do it is to use the full Formlabs ecosystem. And I won't go into too much detail here for the sake of time, and we'll talk a bit more about it later, but it's useful to know that once a print is finished, there is a removable build chamber that holds all of the parts and the powder. And if you're looking for high throughput, you can actually have multiple chambers and sort of cycle them as you're taking one out. But once you remove the part and the powder chamber, you can move it over to the sift, which we see here in the middle. And in the sift, you can dig your parts out, and it's going to capture any of that unused powder and throw it into a cartridge to use in the future. And then for the best surface finish, the last step is moving your parts over to a fully automated sandblasting cabinet. And this thing will clean up any remaining loose powder from those just little nooks and crannies where it's difficult to kind of get to in the sift. And then you can also use it to polish your parts to an almost satin finish. And then it also has a rinse cycle that fully cleans the parts off, so they are finished and ready to use or ship right out of this machine. And so that all kind of covers the SLS process. So let's go ahead and we can dive into a little bit more on the design and software side and how we would set up a really high volume build.
All right, perfect. So knowing how this system works and searching around for parts we could do, I noticed that there are some of these sample parts, specifically this one right here that's like a little Pelican case. And inside you open it up and there's these panels that demonstrate minimum feature sizes. So it's a really cool part. It's all print in place with hinges, but it's a little bit big, so it gets kind of expensive. And it's an absolute nightmare to get the powder out from behind the panel inside. And so it's a very time intensive and material intensive part. So I thought, okay, well, what else could we do on that theme? Pelican does make micro cases, but none of them are really any smaller than about a cell phone. So what I was hoping for was something even smaller than that, something you could put in your pocket. And I thought, well, what are some other things that you either might have floating around in your pocket that you might want to keep safe, you might want to keep on you, or you may need to sort of put them in the bottom of your bag or your purse, and you want to keep these small things safe and near you. So I started thinking about my Mastercam license dongle, earplugs, the dongle or the memory card that's those little headless USB, flash drives, medicine, you name it. there's a lot of things you might want to keep in a very secure case like this. And so we basically built our own design. So let me show you what that looks like. And so here is kind of the picture, right? I took a photograph of the print for that Pelican case that was coming out of Formlabs, that sample part. And I thought, this looks pretty cool. Let's see if we can kind of copy this. And so I started out real simple, right? Create some parts. Let me show you the section view so you can kind of see a little bit more of the functional details. Hollow inside, it's 2 pieces. It's a multi-body part. It has this lip all the way around where the latches are going to latch in. And then as I continued building, I needed to start building a hinge. Now this is where I really needed Bryce's help, because I needed to know what tolerance to give this. Because if I leave effectively 0 tolerance, when it melts the material, it's going to melt across that tiny little gap, and it's not going to have any clearance at all. It's going to be one fused piece. And I need this to be a live functional hinge, just like that sample part. Well, print in place on an SLS is kind of new. So I checked out the SLS design guide that Formlabs gives out. So it gives you a lot of reference dimensions, minimum sizes to be successful, minimum gaps, thin walls, embossed features, debossed features. And this one right here is the one I was looking for, is the minimum assembly tolerances. If you have parts that are intended to mesh or interface after printing, like assembly joints, you want to, at a minimum, give yourself 0.2 millimeters. That's 8/1000ths of an inch. If it's a larger part, there's a possibility that it's going to get hot, and so it's going to melt even more. So you want to go 16/1000ths on those. If you've got some integrated assembly clearance, it's a little bit looser, but I thought, okay, let's try the minimum size. In fact, I even tried to undersize it a little bit, with 8/1000ths being kind of my target. When I come in and click on this, you can see that 8/1000ths. I created a global variable in my part called thickness gap or something like that, made it 8/1000ths, and then everywhere I needed to have that clearance, I put it there. So kind of kept on cruising down the line, creating these various different features. I had another clearance situation here where I want this clearance to be as tight as possible between the pin and the shackle. But then other areas, I want to keep it a little bit wider so that I don't have any problems with fusing in places I didn't expect. So I keep on going down the line. I start adding some additional features to help with the aesthetics and hopefully the strength a little bit. And then here we go with the latch. There's the latch, and you can kind of see that I had to build the latch. Sometimes you build it in an orientation that doesn't make sense because that's where your dimensions are, that's how your reference information is, and then you kind of work from there. And so I had to use some move, copy, body commands to finish this out. Now I did go ahead, and this is kind of a funny but silly thing. I built out one side, this right side, and then the left side I would have to copy everything faithfully to the other side with a whole other set of features. Well, instead of that, I just chopped it in half and then mirrored it back across, and now it's got everything I need perfectly symmetric just by building one half of it. Fun little trick there. Started adding some additional little features. Some of these came later, but I wanted to give you an idea of what exactly we had going on with this part so that we could kind of investigate and learn about how this all went together. So the first thing I did was took my initial design. It's a little different than this, but not a lot. I took my initial design, I saved it as an STL and sent it over to Bryce. And Bryce let me know that he needed it in the orientation where it's fully open so that he could print it in place like that. So the first iteration, the first revision was just learning that I had to export it in the correct position and layout for printing. And to do that, we just used some move, copy, body commands and just kind of folded it out flat. So once we got that, we started going back and forth. I would send him a design. He would print it, give me some feedback, and we would do another iteration. And we kind of rapidly went back and forth like that and learned a lot. So, Wes, why don't you take us through the next step in the process, which was getting it ready to print?
After some trial and error, we had a finished model, and it was time to start producing as many of these parts as we could. So the first step is opening up Formlab's slicing software, which is called Preform. And Preform essentially just takes your 3D model and turns it into instructions that tell the printer how to create the part. So it configures things like print temperatures, fan speeds, and the path of the laser, for example. And so once I'm in Preform, I'll start by selecting my printer, and then I'll move on to the material type. In this case, we're going to use nylon 12 because it's sort of the default, cheapest and easiest powder to use. But there are quite a few other things here, like the flexible TPU material, polypropylene, and even some carbon fiber filled nylons that are ultra stiff and strong. But again, in this case, we're sticking with nylon 12. And then we'll also stick with the 0.110 millimeter layer height. And then for the speed settings, I'm going to stick with default in this case because we do have some fine features within the hinges of this case. If it was a simpler part, I would go with speed optimized, which is significantly faster for printing. But once I'm happy with what I've got here, I can go ahead and hit apply. And now all my settings are in place. And what we're looking at here in the center is a representation of the build volume, or the actual printer, the piece that slides in and out the build chamber. And so we want to fill this thing up, and we want to fill it as efficiently as possible because we are filling, as it's printing, we're filling it with powder from the bottom, and we're working our way up. So we'll start by dragging and dropping one of our little keychains here, and I'll use one of these smaller ones to kind of explain things. But the first thing we want to do is, this would be a very inefficient orientation to print this holder because we're using all of this powder up until the top of this to print one of these. So as you can probably imagine, the first thing we want to do is lay this down flat so we can orient to a face, select this face, and then we want to drop this down as far as we can. And so we're using a lot less powder because now we're only filling up to this point. But we still only have one part here, and we can fit a lot more. We want to aim for a packing density of about 30% in most cases. And we're only at 6 so far, so let's see if we can increase that. And I'm going to move this thing over to a corner. And I'm actually going to come over to one of the other tools, select the case again, and we're going to create a few duplicates. So now we've got 4 of these, but again, we're going way up here and we're not using some of the space over here. So the next step I want to do is use the automatic packing, which will put these pieces as efficiently as it can within the build chamber. And it did a good job, but there is one issue, which is that these are slightly tilted off of the build plate, so you can see they're not perfectly parallel. And that's not the biggest deal for most parts, but for flat faces like this, a very slight angle will mean you can see the individual layer lines as it starts to move up this piece. And so we actually want that to be flat and parallel with the build chamber. So I'm actually going to undo the things I just did. And we're going to use another trick here, which is locking the orientation, the XY rotation of this part. And so that means it can spin around this blue arrow, but we won't get any rotations in the other directions. So now we can do the same thing again. We'll create our 3, and we'll use our pack. So now every one of these is nice and flat and parallel with this build plate. And so now we've got our X and Y areas pretty well filled out. So let's go ahead and optimize this even further, and we can use this array tool to start building up in the Z-axis as well. And the array tool, you can select your spacing between your parts. So we'll get a few of these in here, for example. And if I drop this spacing down, the parts get closer together. You really want to aim for somewhere around like 2 or 3 millimeters. You can go as low as 1 millimeter safely, and that's what we did here. But again, in most cases, you want to increase that a little bit. And then you can just start building this up until it stops. So in this case, we've got 92 of these parts that we're able to build out with just a couple of clicks here, and we could upload that to the queue or send it to the printer right away. And so that's for these smaller cases. For the larger case, we ended up pushing things a little bit further. We packed as many of these smaller ones as we could in because we didn't have enough space to push more out in the X and Y direction. But we did end up sort of flip-flopping the orientation of these cases to fit even more of them in here. And so we were able to get about 25 of each of these cases, the small ones and the big ones, in this build area. And we had a packing density of 23%. So we could actually even fill up some of this excess space like we have here in the corner if we had other parts that we needed to print, which is exactly what we did. We had a couple of customer parts to do, so we added them into these spaces, met our 30%, and that's essentially free area to use. So again, we were all happy with this. We uploaded it to the printer and we were good to go. So the parts came out great, but there were a few things that we learned along the way, which we'll sort of get into now.
All right, so once we get this thing printed, the first one comes off the line. We've got questions we need answers for. I made my best guess on a whole lot of design choices, things like gaps and interferences and stuff like that, to see if they were going to work. In this case, one of the first ones was the fit, right? That snap on that closure is a pretty critical thing. I didn't want it to be so tight that it would break, but I also didn't want it to be so loose that it would loosen up over time and start to fall apart. And so we printed one. My first guess was this one. I'll let you listen to it. It's got a very satisfying snap. And the hinge is a little bit tight, right? It's not just super loose. This other one, right? Very, very loose, not tight at all. The second one was the one I feared I would need to do. It actually ended up being right the first time, giving us a really great design using those standard 8,000th gaps that were shown in the design guide, and about a 13,000ths kind of interference on that latch. Next, we take a look at the thickness and the strength. And the thickness overall was good, but the hinges and pins were all really weak. And so I had made them smaller than the overall thickness of the case, because that's typically how you see it in real cases. But in this case, it's not a metal hinge, so we needed to thicken those up. So the final iteration, the wall thickness was about 70 thousandths. Pin diameter is about the same, and this thing was nearly indestructible. I took this all over the place with me and was constantly doing that. We did do kind of the Napoleon Dynamite thing where we ran it over with a Ford Ranger, but it did not survive that one. I do think it held the truck up for a minute before it crashed, but still. So we've got a good idea on the wall thickness. When it comes to gaps, right, we talked about that tight fit being 8 thousandths. That did a great job. If we want it to be a full clearance where there's no even slight grab, we wanted to make sure a minimum of 14 thousandths is what we found worked pretty well. And in this one, you have to pay attention to all the gaps. And I actually used some interference detection and some clearance verification tools in SolidWorks, because when we would open it up, there were a few faces that I didn't realize got really close. And so we would go through and print some of these. And then once we were done with the depowdering, we would sort of crack it where that 8 thousandths tight fit is just barely held on, but it very smoothly and easily breaks free. Well, that section that wasn't gapped correctly would merge, and then that would break the hinges because you were putting a significant amount of force to break them.
And I will say we were actually able to salvage a lot of these that had that too tight of a clearance. We found that if there was a really specific location and way that you applied the force, you could kind of break it loose. So yeah, we still were able to work with a lot of these. Our thumbs were hurting at the end of the day from breaking them loose. And this one is exactly what I talked about during the preform section, where if the part is printed at a very slight angle, so this one we're talking maybe 1 or 2 degrees, you'll be able to see those layer lines more distinctly because each part of that flat face was printed on a different layer instead of the other parts, which were all printed in one layer, so you can't see those lines at all. And again, in this case, the part was perfectly functional. It just had an aesthetic difference versus some of the other ones that we were working with that we printed perfectly parallel.
And orientation in general also produced different surface finishes. It also produced different strengths. So your strongest direction is for this to be flat and parallel to roller plane, right? The print plane in the XY. And so that worked out really well. We just go ahead and locked those in place for the rest. But you can kind of see, depending on if they're vertical or horizontal, we've got different options. You also, this picture illustrates the design iterations. We did a lot of design iterations, and we made different sizes. We made different kind of containers. So like the bottom one there, that's a business card holder. We tried just scaling it up with the same hinges, didn't feel strong enough. So we turned it into a piano hinge. That was much, much stronger. With bigger latches and everything like that. We created gaps and openings so that you could pull the cards out. But being able to iterate quickly, almost daily, was massively helpful.
Optimizing the print orientation was sort of a common theme when it came to the lessons that we learned, and this is another good example of that. So when this part is printing, and this is our side view, so starting from the bottom here and working our way up, when we reached this point on the tab, it's actually just a floating part. It's an island over here by itself before it reaches the top of the hinge. And so there were just a couple of these out of the whole part run that we did where it shifted over just slightly when the next layer of powder got rolled across. And so it was barely noticeable. And again, in this case, the part was still functional, but I think if it was a little bit smaller of an island, it would have had a bigger risk and it might have actually impacted the part runs. So just one other thing to consider as we're going through this. And it might have pushed us, if we were doing these as a full production part, to only print them flipped over in one direction. But having them opposite gave us just a couple of extra per build, so it was worth it for us. We ran into a similar issue with the emboss versus deboss scenario because at first we tried to emboss these where the lettering actually stuck out, but we found that when we went to brush it, those letters were really fine and small, and we could actually kind of brush them off, or they maybe had already shifted during the printing process. So we found that debossing these really fine letters and sort of engraving them was a better approach. Another thing worth talking about is just your sifting efficiency, because there's a common trap that you just spend all kinds of time here trying to get every little nook and cranny, but really the bulk of the powder will fall off in just a couple of seconds, and the amount of time that you spend trying to get into every little nook and cranny versus the amount of powder you're getting back is just negligible. So really spend a couple of seconds here and let the blast do the rest of the work, because that's really what it was designed for. Blasting went pretty smoothly. There's not a whole lot to learn here except for we tried to load the entire build chamber of parts into the blast at one time, and a couple of them fell out during the run, so not a big deal, but it is something to consider. Otherwise, this thing did an incredible job. I didn't think it would be able to get into every nook and cranny the way that it did, but it saved us a ton of time by being able to do this in an automated way, and that rinse cycle that cleans the parts off afterwards worked out great.
We had some concerns initially about depowdering. So we were afraid that the powder would get stuck inside the hinges and you would not be able to get that out. So in the first design on the left, we kind of designed the pins to be out so that the powder could fall out. And then one of our final designs we did included a piano hinge, which didn't really have any gaps, and it worked perfectly. There was really zero difference that we could identify between those two designs. So as long as there's movement, depowdering was not a problem. If it was a closed section like that and there was no relative movement, then that probably would have some powder stuck in there that we wouldn't be able to get out. As far as cost, it really just boils down to the material and the labor to kind of shuttle them from machine to machine, and kind of the overhead of just the shop operations. So the small cases were right about $1 in terms of the material cost and just the machine running. And then we added another $1 for labor, just to kind of give us a good idea. The larger ones are about $3.50 in material, and so we kind of rounded those up to about $5. Those are ballpark numbers, right? We wouldn't list them at that price, but for internal use, these are very cost-effective cases. And we started thinking about all kinds of other things we could do with these cases. That's why we did the business card holders for our employees from our company summit, and a whole lot of other fun things. All right, so let's talk about how this all played out. What's the outcome here? These cases were a really big hit with attendees. It was such a cool part. We would actually show the process of building the part first, and then at the end of that video, we would hand one out to everybody. And they were like, do I get to keep this? This is awesome, right? And everybody took them home. There was never any left on the table. Most of the time, people would try to ask for more. They had somebody that couldn't make it today, and they wanted one of those. So it was a pretty awesome thing. It was very relatable too, because we showed the process of how they were built. That really helped to communicate and convey that this is a very relatable process, right? We learned a lot in this process, but now we're pretty confident we could make just about any size case we need first try. We've got all the lessons learned of building this case taken care of. We're ready to roll. So like I said, we did the business card holders, we did the giveaways. We've printed well over 600. We haven't kept track completely, but at a minimum from this one main big event we did for Manufacturing Day and Internal Company Summit and some other events, we've printed a lot of these things and given them away, and they're holding up really well. Some additional benefits that kind of get lost in the sauce. Yes, we learned a lot about SLS and about cases and these small keychain size designs. But there was a few things that you just kind of keep forgetting, which is that there was no assembly required here. This is just how they came out, right? We just needed to clean them up and ship them out. The fine text and detail was absolutely faithfully reproduced on all these parts. You could not tell they were 3D printed, other than just the fact that they wouldn't have been able to be produced any other way, right? There wasn't lines and stuff like that all over it. It was a very highly manufacturable design, and by that I mean we just didn't have very many constraints with the manufacturing process. It's not like we were worried about undercuts or draft or any of those kinds of things. We just made a design, whatever design we wanted to do, and as long as we kept those gaps and everything we talked about earlier, and we got the thicknesses right, it was great. It was easy to make from one to hundreds of these parts. This one of the builds we did the most for our company summit. We did 25 small cases and 25 big cases, and that's a one-day print. So printed out, and that was what that cost breakdown was on the cost slide. They're very customizable, so if somebody was doing an event and they wanted, like a commemorative case that said I was at this event or whatever, or you had something specific you wanted to put in there, we definitely could customize that. So we kind of thought, man, if we still used USB dongles for licensing, it would make it really, really cool if when they ordered that license, we shipped the dongle to them with this special protective case, right? Because that dongle is both important to them and valuable to them, but also, it would represent downtime if it got damaged, and you would make sure you always had it on you on your keychain. So we started looking at all kinds of different variations and applications. Some additional ideas we had were things like building custom products, right? This is an actual product we could sell. And in fact, because it's so customizable, we could create an online product configurator using DriveWorks to kind of show the customization and kind of give our customers the ability to say, I want it this size, this tall, this strength rating, whatever you want. And then when they hit go, SolidWorks and DriveWorks would build the model, kick it over to Formlabs, and then we would just batch print whenever we needed to. If you're building big heavy machines and stuff like that, this would be great for replacement parts cases. Right? Just anything where you think, okay, I've got something small and I need to keep it handy. Right? That could be repair parts, little wires, little chips, like the little doodad you use to remove the SIM card on a cell phone, right? Whatever it is that you're doing. Let's do this. Let's open it up for questions. And if anybody wants to learn more about this or has questions about it, please reach out anytime. We'd love to hear from you. I'm going to read through some of these questions and we'll kind of start a Q&A.